Okay, another example is homogeneous ODE, PDE with non-homogeneous boundary conditions. And we are trying to use a modified separation of variables method to solve our PDE in transit. Okay, so another example, so example 2 is homogeneous PDE with non-homogeneous boundary conditions. Okay, and we couldn't use the separation of variables directly because it needs homogeneous PDE with homogeneous boundary conditions. Then we need to do some modification. Let's first elucidate what this example look like. It's still a 1D route, a metal route from 0 to L. And we have that U0T equals 100 degree Celsius, ULT, some boundary conditions, 400 degree Celsius. So at all time, the end of the route will be fixed temperature, and we solve it at steady state before already, right? So we also have that Ux0 equals to Fx, and that is a constant temperature. So that means initially, this temperature, the rest area of the temperature is 700 degrees Celsius. The end of the route will have fixed temperature at all time. And this is belong to a non-homogeneous boundary conditions. And we also have our L equals to 1 meter, that length of the route. The alpha, which is the effective thermal conductivity, is 10 to the minus 4 meter per second square. Okay, meter per second square. So this is our problem site. And we also know that our heat equation in the 1D format is alpha UXX, where this alpha is the effective thermal conductivity, and this is a homogeneous PDE. And remember the assumptions when we derive this homogeneous PDE is that there is no heat source. Okay, there is no heat source. So the Q part equals to 0 for the heat generation or source term. The density, the heat capacity, and thermal conductivity of the rod is constant. It's not changing as function of space or time. So we can derive this 1D heat equation, which is a homogeneous PDE. Okay, just always remember the assumptions of deriving this mathematical equation from the physical properties, and always check whether your assumption is validated for this problem or not. So this is the example, and we are trying to use separation of variables to solve. And using the classical separation of variables couldn't work because it's non-homogeneous boundary conditions. Then we will use a modified version to solve. So what is the modification? Here we derive. So UXT will be equals to Vx of t plus the Wx. Okay, so the Ux of t is the temperature of the rod in the as function of space and time, equals to some function Vx of t, where this Vx of t is a homogeneous PDE with homogeneous boundary conditions. So this is homogeneous PDE with homogeneous boundary conditions. And this Wx is a steady state you can say steady state temperature distribution. So there we can reach the steady state temperature distribution when the time is infinite, when the temperature is not dependent on the time at all. So we can have this Wx where the W is the temperature only as a function of the space. And we already derived this before when the boundary conditions is the fixed temperature. We already derived our Wx, right? So this Wx will be equals to UR minus UL divided by L times X plus U L. So this is the Wx form. We already derived this. Then what we can have, we know this Vxt is a homogeneous PDE with homogeneous boundary conditions. Then the Ut, which is the left-hand side of the partial differential equations, will be equals to Vt, right? And will be equals to alpha Uxx. There is no Wt because W is only as function of space, not as independent of base time. So Ut equals to Vt equals to alpha Uxx. Then what is Uxx? So what is Uxx? What is Uxx? The Uxx is the second order as function of space, will be equals to Vxx plus W double prime. This W is just a simple ODE here. So it's just a simple ODE, which is only independent variable is the space. Then we have the Uxx, so Ut equals to Vt equals to alpha Uxx, and since Uxx equals to Vxx plus omega double prime, that will be equals to alpha Vxx plus alpha W double prime. Okay. Then what we have here, we have since Vxt is homogeneous PDE with homogeneous boundary conditions. That is our assumptions to do this modified separation of variables. And since this assumption, let's assume this is true, then at steady state, this Vt will be equals to 0. Okay. Vt will be equals to 0 because the temperature is not as function of time anymore. Vt equals to 0. U0t will be equals to V0t plus the W0. That is at the steady state. Okay. And we are trying to figure out whether our assumption can be validated or not. So Vt is equals to the alpha Vxx and the alpha omega double prime will be equals to 0 because this as function, this is the steady state function of W. And when you do the second order of the W will be equals to 0. So this part will be 0. Vt is only equals to alpha Vxx. Okay, it's only equals to alpha Vxx. And let's see the boundary condition. So this part is a homogeneous PDE. Then how about the boundary condition? Is that the boundary condition is homogeneous or not? Then we have V0t will be equals to, so we have W0 equals to 100 degrees Celsius. WL equals to 400 degrees Celsius. V0t will be equals to U0t minus W0, then it will be equals to 0. VLT will be equals to ULT minus, so ULT equals to VLT plus WL. So the ULT minus WL will be equals to 0 as well. Then because this W is a steady state temperature, it satisfies alpha W double prime equals to 0, W0 equals to 100, WL equals to 400. Then the leftover part, V0t will be equals to 0, VLT equals to 0, and VT equals to alpha VXX. So V function as function of X and T is a homogeneous PDE with homogeneous boundary conditions, and it's satisfied with our assumption. Then what else? It's falling into the part that since this is a homogeneous PDE with homogeneous boundary conditions, we can use separation of variables directly to the V function. Okay? So we have Vt equals to alpha Vxx with V0t equals to 0, VLT equals to 0. And now we are trying to get this V function using separation of variables. Where the Vxt will be equals to some function as function of only x, so fx, some function as function of time, only time here, gt, with f0 equals to 0, fl equals to 0. This is the Sturm-Duval problem site for the fx, and it's just a simple first order ODE for the GT. So we already solved with the previous example. We just say the final solution here, the Vn will be equals to the sum of Cn sine n pi x over L e to the minus alpha n squared pi squared over L squared t. So this is the derived solutions from our previous homogeneous PDE with homogeneous boundary conditions. Then we are trying to figure out what is our coefficient here. And in order to figure out our coefficient, we have to input some other boundary conditions we haven't used before. So another boundary conditions we haven't used so far is the Ux0 equals to 700 degrees Celsius. So this is the boundary conditions we haven't used. This is also an initial boundary condition. At the initial time, the distribution of the route of the rest area, besides that, the end and the initial route, the rest area is 70 degrees Celsius. And we know that Vx0 will be equals to Ux0 minus Wx, right? And Ux0 is equals to what? Is 70 minus Wx is our steady state temperature distribution, which is 300 x minus 100 is minus 300 x minus 30. So that is our Vx0. That is the only condition we haven't used so far trying to solve what is our coefficient Cn. So Vx0 will be equals to the sum n sine n pi x over L. Since t equals to 0, then this part will be equals to 1, right? Then basically the Vx0 will be just the sum of Cn sine n pi x over L, and that is equals to minus 300 x minus 30. And this looks very familiar. It's basically using the Fourier series to represent a continuous function, where the continuous function is first order of x. And in order to find the coefficient Cn, you just need to get the inner product, right? The inner product of fx sine n pi x over L over the normalization part sine n pi x over L sine n pi x over L. And this sine n pi x over L sine n pi x over L, this interproduct will be L over 2. So the determinant will be 2 over L times the inner product, which is minus 300 x minus 30 sine n pi x over L. And you know that basically you just need to integral from 0 to L of this product of these two functions over dx. Then the final, you can see more detail of the math from the printed out version of the PDE part. The Cn in the end will be equals to 600 over n pi times minus 1 to the nth power plus 60 divided by n pi times minus 1 to the nth power minus 1. And since you know Cn, you know what the rest of your function, you know the Vn, you also know the Wx. Then we know the final Uxt will be equals to Vxt plus Wx, and Vxt will be the sum of Cn times sine n pi x over L e to the minus alpha n squared pi squared over L squared t. That is the Vxt plus Wx will be 300x plus 100. That is the steady state temperature distribution. And where the Cn is equals to the above equations here. And n is from 1, 2, 3 until infinity. And you can program this into the MATLAB, trying to see how the temperature distribution as function of time, as function of space, as you have this non-zero homogeneous boundary conditions.